Well, yeah, you know what this is about. I don't even know who this person is.
Hey gamers, today
Who is this guy? He's neat, and he's like 3 million subscribers, and I've never heard of him before. But besides that, which is just a revelation to me, and I started off in Roblox, which is painful to go back to because I had 100 subscribers and then 200 subscribers and then 800 subscribers and then I died. Let's go to the actual video I'm responding to. You guessed it,
it's
Tyler.
time for some more mega project.
Let's just, get the camera on, I guess. Wait, am I dressed? Nope. Okay, so I need to figure out where the button is and pause the stream. Where is the button, actually? There's the button. It's like in the middle somewhere. Okay, hold on. Am I fragrant? Fragrant? Yes. I did use hair stuff with my hair, so I'm fragrant. Anyway, we'll get into this.
Specifically, this could change science. Could cold fusion replace nuclear energy? Presumably.
Okay, so let's just get decent with this video. Look. I think everyone's seen the Chain Reaction movie, so we know where this is going. Possibly.
Implying that fusion is somehow not nuclear. For those of you who don't know me, I'm Tyler Pulse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is new, but I can certainly share some knowledge. Let's see. Every few decades.
People don't even know what electrons are. Yeah, there's a lot of nuclear in electrons right there. What if you stripped away all the electrons? Wouldn't all the rest of the proton neutrons just fuse together if you push them together? Why not?
Science stumbles across something that sounds impossible but refuses to go away. The details might be disputed, the data might fall apart, but the idea lingers. Wait. Well, that's because a lot of those have powerful incentives, such as limitless clean energy and ambiguous experiments.
Or the ability to make new materials that could be useful in and of themselves without using massive amounts of power to do so. You know, fusion is just the moving of the building blocks of the original parts that are used in regular chemistry, which is moving around the parts. But the components of those parts are the protons and neutrons, and then you gotta deal with the quarks and everything. But in general, you should be able to move around the parts and get whatever you want as long as the electrons aren't in the way. With a little help of a little nudge or something else going on there.
Which, in nuclear engineering, ambiguous isn't good enough. Nuclear reactions leave behind unambiguous footprints.
Okay. I just said it. If you take away the electrons, all you have left is the soup of protons and neutrons, and they're just gonna maybe under pressure become something that's fused together like tritium or whatever. Which, yeah, if we could have that in abundant quantities without using a fusion reactor in order to do it, or a standard high energy velocity system with compression, like if we have a smaller system capable of fusing things together somehow, I don't know. It could happen without using a lot of power.
Is to say specific radiation and isotopes. If those aren't there.
Well, then you're not doing fusion in your big machine ways, in your high power, like shooting neutrons at stuff to make things split apart. No, that's fission. Whoops. You work in the nuclear power industry working with fission, right? Have you ever worked with fusion? I don't know. Let's put individualisms aside.
Then a reaction didn't happen.
Waiting for another chance. And cold fusion. Well, that's one of those ideas, isn't it? In March 19...
A high neutron bombardment interaction reaction didn't happen. Doesn't mean you didn't fuse. Two different things. Like, there is a lot of ways to make like chains of carbon atoms with fluoride or whatever, but I say whatever because I'm not exactly tuned to that terminology, but we all know that any chain of carbon atoms with that stuff was like, oh, we don't want that. But there's a lot of ways, different ways of making the same polymer.
1992, electrochemist from...
Oh, these fine gentlemen here. If you want to hear a much deeper dive on the exploits of these two, I'll pin that video in a comment.
University of Utah.
It was called chain reaction.
Stanley Pons and Martin Fleischmann stood in front of reporters and made a claim that caught everybody off guard. They said they'd just triggered a nuclear reaction in a laboratory using heavy water and a palladium electrode.
So here's the thing about nuclear. Again, in normal chemical reactions, we're talking about moving individual atoms and making them join together by electron bonds. That regular stuff happens all the time. We can do that in chemistry all the time. But in nuclear stuff, we're working with dividing or combining those atoms' parts together. It's like saying that you're going to make a 3x2x4 Lego, which is a standard brick, turn into somehow a multiple 1x2x8 standard bricks, which are the thin ones, and not easy to do. On the normal circumstances, the structure isn't there, so you gotta like jerry-rig it and force it into those configurations in order to make that happen, which usually involves melting the plastic and changing it, but you don't have enough material in a standard Lego brick to make 3 separate pieces. So, fusion.
Example of a huge claim.
Also, if you make fusion of 3 thin bricks into a big brick, you have more material than a standard hollow big brick. But that's obvious for Lego. Why is it so challenging when it comes to actual physics? I don't know.
Without enough reproducible experiments to validate that claim.
The process took place at room temperature without radiation, and it produced more heat than they could explain.
That right there is the red flag. Deuterium loaded into a palladium lattice, producing excess heat, and they attribute it to nuclear fusion. Problem is, it didn't leave behind any nuclear signatures, such as neutrons.
What are the other parts of the palladium lattice? Because we don't ever use pure anything. We use a compound of palladium and maybe carbon?
Tritium, helium isotopes, gamma radiation at a rate that would be consistent with true deuterium-deuterium fusion.
If the claim was accurate, the implications were absolutely enormous. It meant nuclear power without reactors, without high temperatures.
Okay. That's based on the assumption that was going to be fusion creating power. You can do fusion without making power as much as you can just, like, apparently I just recently heard about camels that take the hydrogen and merge it with that is in their fat, merge it with the oxygen in the air and make water that was more than what they had of the fat. And that's just a chemical reaction stuff. That's crazy, and that's very neat, but also, what?
Importantly,
Okay, couple of red flags. Room temperature fusion directly contradicts the known Coulomb barrier. Between nuclei, as in what it would actually take to cause fusion. And no radiation, if you're producing several million electron volts per reaction, like a true fusion reaction, say in the sun, it's not going to be useful. The whole point of having a reactor is you need that bulk, high temperature system to generate enough heat.
The standard energy, there are two ways of generating energy, okay? The reactions with electromagnetism and making heat to make turbines do stuff. Two ways. Helios already does the second method. And the other thing is, what if we just want to fuse stuff together? Who cares if it makes energy for us? We're able to make a thing and then put that thing into the other thing. Right? Product assembly. Could be more important.
To spin a turbine, spin a generator, generate electricity in large amounts.
That's the standard system. It's not every system.
Even if this thing somehow worked, if it's produced so little energy, it wouldn't be particularly useful. I mean,
with a thermal-electric system.
After all, real fusion produces energetic neutrons and activation products. Saying it.
Yeah, if you don't have... Oh, you know where those energetic neutrons come from? Pushing everything in a way that makes them literally eject from their normal nucleus. Guess what happens if you hold them in? You get more reaction, or more able to stably fuse, instead of lost product. You know, neutrons are like half of the material that you're trying to fuse. The protons are the other part. Start using sound. You'll control the neutrons. Then you can fuse without using a lot of heat or using a lot of... Okay, to be clear, sound would also control the movement of the protons because it's just particles held by the standing waves. However, and you can have extreme high frequency standing waves capable of controlling neutrons and protons and all of that, but you can also use the electromagnetism to control the protons and the other part of the electromagnetism to remove the electrons, and then you end up with, well, the Coulomb barrier, which really, what does it take to do that? Hard to know because we haven't tried. And again, I'll claim it that if you're not as fast as quadrillion a second, you're not going to be accurate about these things. So understand there's going to be some uncertainty principle, as they say. But once you are that accurate, you won't have that uncertainty. Okay? So error is expected.
Didn't leave behind any radiation or any radioactive waste just isn't a safe assumption. Just like anything else, it's going to generate waste unless they somehow used an unknown part of physics or magic or whatever.
Yeah, an unknown part of physics, like how no one knows how the electromagnetic field is its own thing and is not just affecting electrons, but it's affecting everything. Because it literally is this thing that connects electrons to protons, that connects everything. That's a easy, instant, you just know that. That's how that works. And what is that electromagnetic field itself? Well, people are yet to even discover my videos, so they won't know for another decade.
What it is they're trying to do.
Without radioactive waste, it suggested that clean, abundant energy could be produced using equipment that fits on a table, not in a power plant.
Again, that's a statement assuming that fusion would create power, but with this type of fusion, you won't make power, but you will make fusion.
And that's where all
Possibly.
the hype started.
For a few weeks, the news cycle ran wild. Newspapers called it a scientific revolution, investors showed up, and political leaders started to pay attention. Then, the replication efforts began.
And any scientist is going to warn against doing something like that before you get repeated.
It's like the guy who said that he thought of X-rays before he actually proved that it was X-rays, because it was just some other reflected light or some other light from some other part of the experiment he didn't account for. However, X-rays did exist. It doesn't mean that it's false. It just means he didn't do the thing, but there is something X-ray out there. We just didn't know yet.
Results.
And the results not exactly encouraging. You probably knew that, given that we're not all just using cold fusion today. Most labs could not reproduce the effect. Leading physicists expressed doubt almost immediately, and within months, the story shifted from triumph to embarrassment. Yep. Cold fusion became
into a movie.
A warning about
became confusion.
Poor experimental controls and premature publicity.
I'm going to allow that.
But even as the headlines faded,
this really is a case study of don't publish your thing too quickly without getting repeated results.
A few researchers...
Hold on. People are talking about entangled particles, and I recently saw Gobbledygook Lady, Sabina, talk about entangled particles, and again, they don't have a correlation effect, but there is no cause effect, but there is a correlation, meaning, yeah, the two parts were made in a way that the two halves are definitely like the two halves of a baseball. They each have the design on both halves and are individual to each other. However, they interact differently because one is exactly the right half and one is exactly the left half of the baseball. However, the word entanglement is still used to this day, and it doesn't happen.
Working quietly. Some of them reported unusual results that never made it past peer review. Others claimed to measure heat that they could not explain.
That's true, there's still a small community out there, but anecdotal,
Again, heat that you can't explain, like, there's a lot of things that can make heat besides, like, any amount of motion in the soup is heat. So, yeah, if you can make things that happen, there you go, you got heat. Also, let's keep listening.
Peer-reviewed reports just don't mean a whole lot.
Over time, the phrase cold fusion was replaced with something more cautious: low-energy nuclear reactions, or LENR.
Have to rebrand it.
Fast forward to 2025 and the conversations started again. This time, it includes military labs, government grants, and serious scientists who believe the topic deserves another look. There is still no consensus, but there is no longer universal dismissal either.
Is it just me, or is he a little more... I don't know, he seems to be a little...
Why does this sound like it's the end of the video already?
More into the whole ASMR
We're 2 minutes
triggering narration. Kind of reminds me of some shows on NPR.
So what exactly is cold fusion? Why did it attract so much attention, and why did it fall apart so quickly? Most importantly, is there any reason to believe...
Listen, you could pay for it.
I won't.
Most importantly, is there any reason to believe that it might actually work? Well,
so only if a rigorous, blind, independently reproducible experiment shows excess heat significantly above chemical energy balance.
Fuck your ideas of heat. Screw it. We have made a Bose-Einstein condensate that has cold. Why can't we make fusion in that condensate? Question mark. Point.
And corresponding nuclear products at rates consistent with the energy released during the fusion reaction.
Reaction products happen due to negligence, perhaps, of like not accounting for all the parts, like how we let neutrons just fly off and do nothing, and then we end up with a bunch of stuff that's like broken because we're negligent, lazy, stupid scientists making a goddamn toroid machine which makes things spin really fast and turn into a plasma and whatever else, when you can do a lot of other things to remove electrons from the equation, but then also take all of the material. If I took 1,000 hydrogen atoms, I could make a couple uranium with the right equipment. That's just the future of things. Get over yourself.
And to date, those two boxes have not been reliably tested.
Let's go back to where it all began. The promise. Cold fusion proposes something extraordinary, a nuclear reaction that happens near room temperature. Unlike traditional fusion, which takes place in the heart of stars and inside experimental reactors using ultra-hot plasma, cold fusion would occur in a small lab environment with no massive heat, no glowing chambers, and no radiation burn.
Just controls of the electrons. Both ways can work. It's just, are they doing it?
Which is nice for the scientists. That contrast is at the heart of its appeal.
Yeah.
Traditional fusion forces atomic nuclei together by blasting them with it.
Yeah, the blasting part is where you get the radioactive parts. Not really subtle. Not really, what do you call it? Delicate work.
You need magnetic fields, vacuum systems, and machines the size of buildings. And even then, most experimental reactors consume more energy.
What's interesting is the sun has comparably cold fusion at a temperature of merely 15 million degrees Celsius compared to the temperatures in excess of 100 million degrees Celsius you need on Earth.
And again, Helios, they made a reactor that is, again, forgetting about the fact that you can just remove all the electrons in the first place and then move all the material. But then the thing is, you do two things with that reactor, right? You make it super hot. I don't even know if you remove all the electrons. You don't control the neutrons. And you like smash them together to hope that things stick. It's a lot of velocities involved. And twice velocity, because they smash from both directions, means more reactions possible. And then after that, you have this glowing ball that you're holding with magnets all around it in order to heat it and keep it pressured and squeeze it. And then the adverse pressure of any reactions that take place, the bumping of the electromagnetic field, that holding confinement field reactions, that energy is then able to be gathered by their systems, and they're getting like 50% back. I don't know about you, but 50% is a whole lot better than anything else anyone has ever done. But the problem with the tokamak is they have never made a system designed to make power with a tokamak. They just want to start the basic concept of fusion, do a thing. And the amount of heat and stuff, we can assume the amount of power that we could make. But we never attached a damn machine to make power with this thing. Because it runs for like seconds and whatever. Crap.
Just because of sun's high gravity, it can get away with self-sustaining fusion reactions at a relatively low temperature because its gravitational force is so strong.
Energy that they produce, which isn't much good at all.
And also, the sun has a ton of Earth's worth of material to do fusion with. So the amount of reactions are based off of all those different potential parts doing their combining in those conditions. Otherwise, we need to do a lot more in order to achieve the same thing. And we're trying that, although we're failing. And we're not using sound, which is the main problem with all of this stupidity.
Fusion works, but scaling it for energy production has proven slow, expensive, and unpredictable. Cold fusion suggests a shortcut. That begins with hydrogen, often the isotope called deuterium, absorbed into a metal such as palladium. As the
So a single proton, 2 neutrons.
hydrogen atoms settle into the spaces within the metal structure, something unusual may happen. Some researchers believe that under the right conditions...
Okay, I'm gonna just spit on your face right now because that whole oxygen-looking thing, that's not how that works, although it is. I guess it is. No, that is what it is, because the deuterium is the oxygen and the... But it's the water, it's a heavy water because of the extra neutrons in the hydrogen parts. Okay, whatever. You're working with water and that. Again, water can have its own heating functions.
The atoms interact in a way that produces heat. This heat, they claim, is far greater than what could come from ordinary chemistry. What makes these claims intriguing is that in some experiments, the excess heat appears alongside helium or trace particles that hint at nuclear reactions. However, these reactions do not release the harmful radiation one would expect. That gap, the presence of possible nuclear effects without typical nuclear side effects, is what continues to puzzle researchers.
So what can happen in this electron screening in a metal lattice with something like palladium can modify the absurdly low probabilities of tunneling, but not by factors of several million that would be needed to cause fusion. And it would have to produce radiation. Fusion produces radiation, which is a good thing. Otherwise, the sun wouldn't take care of us very well.
I have a candle. I don't think you're making a good claim there. Because you don't need proper radiation. The candle itself is not making radiation. Well, it is. That's curious. Now that I think about it. But it's obviously making infrared radiation besides the fact that it's making light. You can make candles that don't even make light, but just the infrared radiation. That'd be fun.
The nuclear signatures have to be present.
Now, if the effect is real and can be understood, the consequences would be far-reaching. It would mean energy production without smoke, fuel combustion, or waste byproducts. It would require no uranium.
In other words, some sort of crazy 100% efficiency sci-fi reaction that has never been seen through any forms of power generation.
You're not using sound, then you're not at my level. So, yeah, sci-fi considered? Okay, but a lot of people don't understand how sound, and it's literally the only way that you can hold neutrons. So, yeah, you're not doing due diligence as an experiment whatsoever if you're not using sound.
Just nuclear.
No radioactive decay, and
no, fusion wouldn't involve uranium at all either. I mean, good luck trying to fuse uranium. Sorry. It's a big one. It's the one you want to split and use in a fission reactor.
You know that carbon-14 does nuclear decay. Shut up! For a second there. I need to rewind that and listen to it again and make sure that I'm not wrong about this, because you don't need uranium to do decay. You can do it with carbon. Excuse me, buddy.
Sci-fi reaction that has never been seen through any forms of power generation, not just nuclear.
No radioactive decay, and
no, fusion wouldn't involve uranium at all either. I mean, good luck trying to fuse uranium. Sorry. It's a big one. It's the one you want to split and use in a fission reactor. You shouldn't be anywhere near uranium on your periodic table when doing fusion, cold or otherwise.
Massive turbines. Instead of needing a grid fed by power plants,
Okay, so ignoring all types of radioactive decay, the very simple one is from carbon 14, 13, whatever, 12, 11. That kind of stuff is very simple, right? Certain amount of neutrons in there, and then it decays into the less amount of neutrons in the carbon. Very simple, carbon dating, basic stuff. Whatever.
each home or building, in theory, could become its source of power.
Okay, so not only are you saying we're going to do away with a big nuclear plant as your heat source, we're just going to do completely away with power plants altogether. And this was going to be the equivalent of having solar panels.
Listen, any amount of thing where you're talking about the amount of power is possibly to generate power, clearly it would power itself first, and then any excess power goes out. Because what's the point of putting power in if you have to put power, more power out? Instead, you would just cycle it and take the excess. And that excess needs to be in excess of, like, literally anything. But it has to be considerable amount per the size of the facility that you're using. So if you're using coal, it's crap. If you're using nuclear, it's a lot. And if you're using this, it could be less than coal, but it could be cleaner. We don't know.
In your house or something like that, just with cold fusion.
Or I should say, I haven't heard anything about
that's
the
also
right now.
100% efficient. Just putting all your house loads up to this thing. No need for maybe having a fusion battery or a little cell.
Energy infrastructure would shift from centralized mega projects to small, efficient systems that serve local needs. This has implications beyond cost or convenience. Cold fusion, if proven, would upend existing assumptions about energy security.
Alright, so even if it
So in other words, it would push back on coal even harder than nuclear is, and it's failing to do. And again, when you're talking about hydrogen, there's a bomb named after hydrogen. Wonder why that is. Very negative results. But
it worked the way you claimed, saying it's going to completely, you're going to get rid of large-scale energy production and just...
what about, here's a random thing. I thought about it in the shower. What if you took electrons and tried to make them into a star? I know that electrons repel each other. So to make an electron star, you have to have something that holds them and binds them together. Could the gravity of the electrons just being all in the vicinity of each other be enough to overcome their negativity? And like, you can make a string of electrons, and the electromagnetism, if it would be allowed to, can flow in one end and out the other in like a positive and negative. And the reason why positive, a spin up and spin down are the most common occurrences, because guess what? That's how the electricity likes to flow. The electromagnetism likes to flow in a nice circle. Spin up, it flows positive, it flows north. Spin down, it flows south. That makes a circuit. Real simple. Fluid dynamics.
everyone's going to have just their little cold fusion thing at home. No. I mean, people have modular solar and even in some cases modular wind for their own.
Don't compare any amount of fusion or energy reactive batteries and whatever else. We already have batteries, okay? They're already doing weird stuff with reactions concerning electrons and whatever materials the batteries are made out of. Usually the anode, cathode, whatever stuff, or blah. It doesn't matter because batteries already exist. So we already have standalone, doesn't use anything, energy providing thing. It does heat up a bit, and that's not fusion, and it's power. It's powering my phone right now, but it's not like freaking solar panel, which is only available in the sunlight, and it's not wind, which is only available in the wind. It's forever, because as long as it's maintained. So yeah, you have batteries, you can do stuff with that. Clearly it won't last forever. You have to do stuff to maintain them, refurbish them. But no one does that. They just throw it out. They throw out the entire machine.
House. But that hasn't done away with large-scale solar and wind production, just because of how...
But also we have thermal energy power, where you're just heating up a bunch of sand, and that makes a power battery. Or you have, like, put a bunch of inertia into a spinning flywheel, and then that slows down slowly, generating power for the system, either through giving its own rotational energy to the system slowly. Because, like, that speed can be fed into a much geared down system, so that all of its motion does a lot of action with a lot of force, mind you, without actually having to dissipate its own inertia quickly. The more you try to pull out of it, the slower it gets, and then you gotta speed it up again. But that's another type of thing. It's also not consistent yet.
Economies of scale work. That I don't even see the reason to go there, but I can kind of understand some of the hype during the Fleischmann and Pond days. Maybe that's what he's referencing.
Development planning and international competition. Countries with little access to fossil fuels or nuclear facilities could generate energy independently. Climate targets would be easier to meet.
That assumes they have access to whatever magic you're working with in this cold fusion experiment. So apparently that needs to be evenly checked between all country. Whoever set up the Earth checked the strategic balance icon for cold fusion before starting their game of civilization.
Be right back. Whenever I find the button.
Starting their game of civilization.
Not painful trade-offs. Emergency power systems could become far more reliable, far more compact. The materials involved, they're not rare. The setups, if viable, would not require billion-dollar investments. Instead, power could be drawn from devices.
You know that if you can do basic fusion without needing a giant reactor or a powerful reactor, that if you could just squeeze things together enough, with enough pressure or whatever, natural forces that form them to be pushed together, you would be able to make the materials necessary to do literally anything that you want. So you could start with random material and then recombine it into whatever other material you want. Turn my plate into power, turn something else, my waste products, into a plate, whatever you want. There's no reason to not have that be a possibility. It's just Coulomb's law and all of that in the way. Which, the moment we overcome that by applying a little nudge, which is really all it takes. Well, it takes a little more than a little nudge, but take something like that. You can make a tiny microchip-sized reaction chamber thing that fits in your watch. That fits in a button in your watch.
Size of a suitcase, or smaller, with a few moving
A
parts.
suitcase or smaller. Ha! I talk about a button in your watch, and he's talking about a suitcase. You have no idea what it takes to do fusion. In the most simplest terms. If you're able to do it, again, a button on your watch. That's how small you can make these things. That's crazy. I don't care how crazy it sounds.
No emission.
All this is fantasy.
Use cases for rural hospitals to solve.
Even if cold fusion somehow worked, this is just kind of a whole different thing. Not only does the technology work, but this vision for miniaturized power sources for everything. I mean, it's possible.
We already have radioactive diamond inside of a non-radioactive diamond casing to be able to get the radioactive emissions out of it so that you can make tiny little irradiated batteries that can make power for tens of thousands of years. 10,000 years. I don't know, however long it takes for a regular decay to fully be done. And instead we're trying to do reactions that literally shrink it all down to let's make it last only 100 years. I'm sorry, what?
Free to have situations like this, but it wouldn't be used by everyone.
Zones, space stations, and underwater operations. Just anywhere that the traditional grid just can't reach. The science...
Okay, it would be helpful where the traditional grid couldn't reach, kind of like RTGs, radioisotope thermoelectric generators, are used for things like space probes and remote Arctic weather monitoring equipment that you just don't want to send someone out to connect it to the grid or replace it very often.
Yeah.
That makes a little bit more sense.
Remains unsettled. The potential scale of the reward
Can't rely
is
on
what
Calfarts
keeps
to do it.
interest alive. Few ideas offer a return this large for an investment this small. If it works, that is the
If it
reason
works.
cold fusion hasn't disappeared. It explains why some scientists continue the search, and it shows why the announcement in 1989 triggered such an overwhelming wave of excitement. People were not responding to the hype, they were responding to the scale of the promise. After the announcement, the momentum kicked in. Cold fusion made headlines around the world, with major newspapers calling it the most important scientific discovery since the splitting of the atom. Cameras followed the two
We
chemists
take
from
this
electrons to
long
TV
in the
studios.
video
Journalists
in order
asked whether
to
it would
explain
solve the energy crisis. Commentators speculated
just
that oil and
the
coal might
beginning
become
of the
obsolete within a
story.
decade. The idea caught.
There you go. Keep saying it's 10 years away. Even if it was, it wouldn't obsolete anything that quickly, and maybe keep saying it's 10 years away so you can keep your funding up.
Far, not just because of what it claimed, but because of how much it seemed to promise. A low-cost, clean energy source that could be built on a lab bench.
And again, you don't have to make a low-cost clean energy source if you could make a repeatable energy source. Who cares what the cost is? You did it. We can use this forever, which we can't do with everything else. We're burning everything else. We're eroding everything else. We're removing everything else from everywhere and ending up with eventually 200 years in the future, we have nothing left. That's what we've done to ourselves. So trying to make something that can be consistent, who cares how it happens?
That was really hard to ignore. But inside the physics community,
That's the
mood
bigger
was
picture.
different. Physicists who worked with fusion
I like that it was inside the physics community, implying that people who actually know things about physics know this is a scam.
every day were skeptical. Fusion, as they understood it, came with unmistakable signs. It gave off gamma radiation. It produced neutrons. It left clear, often dangerous footprints.
So it's interesting. So cold fusion, if it did work, it also wouldn't be anything like nuclear fusion if it didn't release any sort of fusion-based heat without nuclear reaction.
The Utah announcement mentioned none.
Again, those kinds of reactions of radiation at small enough scales is hard to distinguish from background radiation. If you're working with something that you suddenly make a blip that is, unless you are detecting it at the source, you're not going to detect it. And you have to cancel out all the rest of the noise in order to detect it in the first place.
There were claims of heat, yes, but no hard numbers, no nuclear signatures.
And the thing is, those numbers are pretty well known. After all, if you're doing deuterium-deuterium fusion, it's going to release about 4 MeV per fusion, which figures out for per watt about 1.6 times 10 to the 12th power fusion reactions per second, which would correspond to a neutron flux of about 8 times 10 to the 11th power neutrons per second. Say half of the deuterium-deuterium branch goes to the neutron branch.
If you're allowing the neutrons to fly around.
And that emission rate would produce, even on a small setup, a very large, easily measurable neutron flux. Neutron detectors would go off, gamma detectors, you'd be able to tell it just by having a Geiger counter.
Immediately raise.
Yeah, and if you stop the neutrons from moving around, with sound, the only way you can hold neutrons, the only way, then you don't have the neutron radiation. You only have the gamma and other types. Infrared. Whatever.
Questions. In labs all around the world, scientists began to test the idea for themselves. Universities and national labs attempted to recreate the experiment. Some had access to similar materials, some even spoke directly with Fleischmann and Pons. The early attempts were promising enough to keep going, but as the replications increased, the results became harder to defend. Many labs found nothing.
Yeah.
Others measured small amounts of excess heat but could not rule out measurement error. Some teams saw fluctuations that seemed interesting but never appeared again. The effect was inconsistent and fragile. There was no clear recipe, no pattern, and no way to tell when or why it might work. Without reproducibility, confidence collapsed. And then came the public response.
And also the other thing you have to consider is, what about neutrinos that are going through the Earth? And if you have your facility shielded from those, does that change the reaction rate and whatever else? And should you be doing it somewhere where there are less or more neutrinos? Why not? And whatever else. You got to consider all possible things that could cause, like cosmic rays type stuff, that can cause interactions on a very small scale like this. And of course, that is only going to happen best if those interactions are in the environment where they can flourish. And if it's not there, then clearly you got something else going on.
From governments and academic institutions, the Department of Energy organized a special panel to investigate. Scientific journals declined to publish the original data, citing a lack of peer review. Physicists
Again, if you want to see my full thoughts on the scandal behind all of this, please click the video in the linked comment.
criticized the decision to go public before the science had been vetted. The announcement had skipped every normal safeguard. That looked less like a discovery and more like a publicity stunt.
Yep.
As the scrutiny deepened, more problems surfaced. The experimental setup lacked proper calibration. Control experiments were missing. Some of the reported heat may have come from chemical reactions and not nuclear ones. The instruments used to measure temperature.
All just implements of just sloppy science. No control groups, no isolating the source of your experiment.
Were not accurate enough to detect
Not isolating your neutrons.
the small changes being claimed. The theory behind the reaction was
Even back then, instruments were pretty sensitive, so claiming they weren't accurate and they're not detecting any sort
They were not accurate. Shut up. They were not. I don't care. No one had sensitive enough equipment because you weren't working with quadrillion per second equipment. No one had that. No one is doing that. There are very few, a handful, maybe 5 ever, experiments that have worked that significant amount of accuracy. So don't say we were ever accurate. It doesn't matter. We just know that the inaccuracy of that is inherent in the process. Ugh.
Of course, the radiation, it's simply because they weren't making it. As in, this wasn't...
Again, neutron detectors only work when the neutrons fly in the direction of the detector, or bounce off something and then eventually fly into the direction of the detector. A bunch of neutrons can be flying out, but the detector itself only registers so many of them. But there are so many more that are happening in all the other directions. So take whatever you scan, multiply it by a factor, and you have the actual number of reactions that you should be seeing or are actually occurring. Something like that.
Fusion.
Ego best. Then, the entire case began to unravel. Within months, the story had reversed. Media outlets that once praised the announcement were now highlighting the backlash. The same journalists who called it a breakthrough were asking how such a mess had made it to national headlines. The shift in tone was harsh because public interest
And we still believe in entanglement, which is a hoax.
disappeared. Research dollars
They gave a Nobel Prize to people who thought an entanglement was real and it's a hoax.
vanished. By the early 1990s, cold fusion had become a cautionary tale. Fleischmann and Bonds, once celebrated, were now avoided. They continued to defend their results for a time, but stopped making public appearances. Scientific conferences would not host cold fusion panels, and major labs stopped investigating. The term itself became a punchline in some circles. To most of the academic world, the case was closed. Cold fusion had started as a possible revolution. It ended, at least for the moment, as a warning about rushing science into the spotlight before it was ready.
And that's essentially the lessons that I learned about it when I even remember it as a case study in physics classes that I took in undergrad.
Even after the collapse of cold fusion's reputation, the idea didn't completely disappear. While most of the scientific community moved on, a handful of researchers
hope it's
continued
still
the
good.
work.
I got it
They
from
tested
the
small setups,
hospital,
refined their methods, and collected data. Their labs were underfunded, often overlooked, and rarely part of any major institution. But the experiments kept going. And what they found was not proof, but it was not nothing either. From time to time, they
Interesting.
recorded temperature increases that did not align with known chemical reactions. The setups were often similar. Palladium electrodes soaked in deuterium, monitored for changes. And in many cases, the heat levels were minimal. But in a few cases, the results were strange enough to prompt further testing. Because the term cold fusion had become a scientific red flag, these researchers began referring to the work with a new name, Low Energy Nuclear Reactions, or LENR. It was more neutral, more descriptive, than it left space for uncertainty.
Okay.
Rather than claiming a breakthrough, it referred to a collection of unexplained observations that might involve nuclear behavior.
Sure.
For many years, LENR research remains on the margins. Peer-reviewed journals rarely published it. Funding was difficult to secure. But a slow shift began to take place. By the early 2000s, a few government agencies started paying attention. The US Navy and DARPA supported small investigations into LENR-related heat effects. These studies
Helios.
focused on understanding whether the observed signals were real and what mechanisms might be responsible.
Had nothing to do
Laser
with it.
stimulation, metal loading ratios, and isotope measurements became common areas of focus. In Europe, interest emerged through research frameworks like Horizon 2020. Projects like Clean HME, based in Poland, brought together universities and private labs to study LENR phenomena using improved tools. These efforts emphasize better calibration, more rigorous data collection, and an emphasis on eliminating noise.
It's still
In Japan,
good.
university labs received backing from tech companies to conduct controlled experiments on hydrogen absorption and thermal anomalies.
So, some things that can happen that can generate heat that have nothing to do with fusion associated with this experiment. As simple as electrochemistry, recombination, hydrogen absorption or desorption, corrosion, or instrument calibration issues can generate heat or spurious signals that could look
Recombination? Question mark?
like excess energy. But
Excuse
without a radiological signature and without the energy needed for fusion, it isn't fusion. I mean, I can understand
know.
getting excess heat from
Can't say that.
an experiment, but thermal energy at room temperature is 0.025 electron volts, which is more than a factor of 10 million smaller than what you would see for a deuterium-deuterium fusion reaction. So unless you're seeing heat generation that's that much bigger, it isn't.
Look, again, heat is the motion of materials. So if you're working with, for example, individuals, or if you're working with only certain conditions, heat has to be transmitted. And if it's not transmitted by something, obviously the setup was like some weird water that has the heavy hydrogen, right? The deuterium. Clearly, if we're ending up with regular hydrogen coming out of it, then neutrons were released, and that can lead to other neutrons going and combining with other things that's semi-nuclear. It doesn't matter what heat you use to get it. The amount of heat that's necessary for individual reactions, tiny. Minuscule, insignificant, irrelevant. You're not going to do anything with an individual reaction. Duh. But what is actually happening? Let me see.
And that's probably for the best, because heat energy, when these little experiments, some of these pictures, some of these little setups, without putting things in place like radiation.
Again, you don't need radiation to make all this work.
Shielding, that's going to be hazardous to your health, to be exposed to even a modest neutron flux. Not the same neutron flux that you would see in a nuclear power plant, but neutron doses scale higher per unit of energy compared to, say, gamma radiation, at least as far as the dose's effect on the human body. It's 5 times more for a slow neutron and 20 times more for a fast neutron. And any fusion.
And if you're able to have the neutrons move around without being super speeded, then you don't have that kind of radiation to worry about.
And at scale, just like any fission of scale, you're going to have a spectrum of both. How much depends on the reactor design.
In the United States, ARPA-E began allocating funds to investigate possible LENR signatures in solid-state systems. Now, these experiments were tightly focused. They were framed as inquiries into basic physical mechanisms, rather than chasing energy.
I don't have a problem with people asking questions, though, for further understanding about heat generation. I don't have an issue with that at all.
Good.
But claiming it's some crazy.
I mean, by rule of thumb, we should know all these types of reactions so that we can know if they are going to happen, maybe that'll inform us about how to avoid them or utilize them in the future to make either slight more efficiencies or avoid catastrophes.
Crazy energy source and you're doing fusion, and that's specious at best without the evidence of radiation.
Applications researchers aimed to understand if nuclear-level interactions were possible under low-energy conditions. The outcomes were cautious, but the interest was real. By 2025, LENR was still far from mainstream, but it had carved out a narrow space in scientific inquiry. It existed in small labs, in specialty conferences, and in government-backed programs that preferred to ask questions rather than declare conclusions. The headlines were gone, but the experiments had never fully stopped. And slowly, the field began to rebuild its footing, one cautious paper at a time. The evidence. So far, the strongest recurring observation in LENR research has been the detection of excess heat. These experiments typically involve palladium, or nickel lattices loaded with deuterium.
Hold on. So literally in this, you're saying these are the results. That is fusion. Shut up, you did it. The amount of heat that you can make out of that, if it's a small enough amount of materials, yeah, you're going to not make a lot of heat. First of all, the amount of heat that you would make can be easily dissipated in the amount of water that you're using. So all of that isn't going to get really warm, depending on the number of reactions and whatever else. So, yeah.
Or hydrogen. Under the right conditions, some of these systems generate more thermal energy than can be explained by chemical reactions alone. The results.
Chemical reactions, again, have to do with the parts that are already built atoms coming together with electric repulsion. The electrons they share or release, molecules coming together and breaking apart and whatever else, acids, bases, all that stuff. This is a completely other thing, and it is nuclear. So you're saying that there is evidence of nuclear without needing to have all that big stuff. The results are there. It's conclusive.
Vary widely in strength and are not always repeatable, but even so, the number of
That's just it. They're not repeatable.
reports over the years has kept interest alive. In
Don't
some cases,
I don't care about repeatability as much as you might, because the specific conditions in order to create the electron stripping and then the deuterium turning into the different components that we saw in that picture. I should take a picture of that, really. Because this... Where the fuck is it? Oh, fuck off. Where are you? Where's the stupid... What? There it is.
so far, the strongest recurring observation in LENR research has been the detection of excess heat. These experiments typically involve palladium or nickel.
Again. I'm gonna just have that for my own information.
lattices loaded with deuterium or hydrogen. Under the right conditions, some of these systems generate more thermal energy than can be explained by chemical reactions alone. The results vary widely in strength and are not always repeatable.
Again, helium into hydrogen, deuterium into hydrogen, all of that stuff, that's still nuclear. The fact that it's been recorded that it's that means that it is nuclear. It's just...
But even so, the number of
That's just it. They're
a
not
different
repeatable.
method.
reports over the years has kept interest alive. In some cases, researchers have measured small amounts of helium, minor traces of tritium, or subtle shifts in
Small amounts of helium,
Yeah,
tritium. Again, you're just orders of magnitude short to explain it, but
I don't care about orders of magnitude. I care about results.
nuclear fusion.
isotope ratios.
The classic nuclear fusion thing is a gigantic tank doing a bunch of things. This is a very small beaker. We're expecting small results.
These are possibly nuclear byproducts and baked.
The numbers I've heard were on the order of single-digit to double-digit electron volts, which is more than what you'd expect, but not the millions of electron volts that would truly fingerprint this.
Do sometimes accompany the reported heat. However, the signals
Again, individual reactions throughout the entire beaker aren't going to give off enough heat that they're going to do anything to the rest of the beaker. It's possible, that it could just dissipate immediately, or be too muffled so it doesn't actually make any heat whatsoever. You could have a system that's so gyroscopic that it moves around enough that its static normal amount of heat doesn't increase, or the motion doesn't increase, right? Or it increases for a fraction of a second and it goes back down because all the rest of the motion is all pushing around each other. You can't, in order to make a certain amount of consistent heat, you have to have consistent reactions, multiple of them, lots of them, in a bigger container doing more things. And when it comes to hydrogen stuff, you don't want to do the big amounts of stuff until you know what you're doing in the first place. And the fact that we have any results means we already have results. They don't have to be
They're
big.
often faint, and independent confirmation has been difficult. At the same time, another detail remains puzzling. Traditional nuclear fusion releases high levels of neutron radiation. LENR experiments, in contrast, show neutron levels that rarely exceed background readings.
That's because the neutrons are actually just... Okay, if you have all the parts and you're not bashing them around, you're just allowing them to possibly combine, the neutrons aren't flying off, you're just merging the soup together, and yeah, they'll make the individual parts, and whatever other neutrons, if they're able to float around, could just combine with other parts. Unless there's some, like they say, the Coulomb reaction, which makes it so that they won't just combine naturally, then how do you explain the fact that we end up with tritium or hydrogen in the first place? And would that not mean that tritium and hydrogen is a chemical reaction? Or a chemically inducible, like a nuclear reaction? Like, the thing I'm stuck on is Coulomb's law, and all of that to do with how these proton-neutron bundles want to fuse together or want to naturally form a bond. So you end up with some that just have the protons go off and do their own thing, and that's the hydrogen, and the remaining components are the rest of the stuff clumped together to make tritium or helium. Right? Pairs. Proton, neutron, then you get the electrons away from each other. It's easy to snap together and make helium. Why wouldn't it? It's the whole idea of there's also this binding stuff surrounding the atom itself that even if you take the electrons away, there's still this other thing stopping the two pairs to become a single thing. But we're seeing it anyway.
The gap continues to divide opinion. The presence of heat and helium suggests a nuclear process could be involved, but the absence of neutron radiation makes that conclusion harder to defend.
Yeah.
For many physicists, this mismatch...
The absence of neutron radiation says that you're doing it right without the stupid inefficiencies. Good job.
remains a barrier to acceptance. Despite the doubts, research continues across several countries. At MIT,
It's all about you have to see the right quantity.
And the other understanding is how much of the deuterium is 100% deuterium and how much of it is it already hydrogen and not deuterium. Right? What if you have mask, like you have not purified the deuterium so it's 100% deuterium? What if you end up with water with your heavy water? Right? How accurate are these things?
Of helium, the
You
right
gotta
quantity
know.
of tritium.
scientists have used calorimetry to study deuterium-loaded palladium cells. Their experiments focus on eliminating error margins and testing for repeatable patterns. In Japan, Clean Planet and affiliated university groups have partnered with private companies to examine small LENR devices. These teams are working in carefully monitored conditions using advanced detection tools and strict protocols. In Europe, the Clean HME project remains active under the European Commission's funding structure. Their objective is to explore the physical mechanisms behind LENR-like effects. They're not developing reactors. Instead, they're running controlled tests with improved instrumentation, including neutron detectors and isotope analysis tools.
That's a step in the right direction, having the right instrumentation and controls when monitoring your experiment.
States, the Army's Cold Regions Research and Engineering Laboratory has taken a particular interest in LENR systems. Their work involves hydrogen and palladium setups, simulated with lasers and observed using high-resolution monitoring.
You could tell the Nuclear Regulatory Commission isn't taking it as seriously because they're not classifying these as reactors, because they know they're really not. They're just small-scale experiments.
Utilizing lasers is more components into this thing, and possibly can be used to be proper measurements, or interfere with everything, or interfere in a way that is constructive and makes it better, or makes it more accurate.
Projects are supported by internal Department of Defense funding and are designed to remove ambiguity from the measurements. Meanwhile, several companies have moved into early-stage development. ENG8 in the United Kingdom, Orion in Canada, and Prometheus in Italy all claim to be building LENR-based energy devices. Most of these involve nickel and hydrogen systems. However, few have released peer-reviewed data, and most remain in prototype form. As of 2025, the call for renewed investigation is gaining momentum. Brian Josephson, a Nobel laureate in physics, has repeatedly supported LENR research. He and others from institutions like MIT and Cambridge have signed public letters encouraging further inquiry. These bills do not...
It could just encouraging further inquiry. It could just be a matter of, let's put this to bed once and for all.
I want the answers. I don't care for... there's no reason to have unanswered questions. And the other thing is, if we want tritium to be doing stuff, and we don't need to be using a reactor in order to make it, that means that we can then use the tritium in reactions with the Helios that they already have and want to do, so that we can just have that stuff that does then do the reaction thing. This can be a manufacturing system. It doesn't mean we have to use this to make power directly. It's another process that uses the substances that are the byproducts of this that are able to do the thing that we want to do.
Everyone kind of gave up, and this could just prove once and for all that it doesn't work.
Claim that LENR has been proven. Instead, they argue that the observed anomalies are too consistent to dismiss outright.
Again, we want the answers because, one, it helps for increased safety overall, so we know about these reactions, we know how to expect them, and we know what they would do if we do stuff that, and whatever, in another thing. We want to make sure that this stuff doesn't mess everything up. We don't want random variables that are able to make everything, maybe explode.
The mystery remains unresolved, but the recurring signals, the slow expansion of interest, and the gradual return of institutional support all points to the same conclusion. While science is still far from settled, the question's no longer ignored.
You still don't know how electromagnetism works, so yeah, a lot of it is undissolved.
And even with all the skepticism, a few theoretical paths have remained open.
I'm not sure what's actually driving the renewed interest in it. I think it just has to go back to the alleged promise.
What is there are math problems that are less interesting and less useful, that have more infrastructure put towards their answering than any of this stuff, which is, if true, actually useful. We don't care if we're doing it and it's useful. We care because it's a question and we want the answer.
Of having a really abundant source of clean energy without as many of the drawbacks, allegedly. Ultimately, even if it did, energy does not equal infrastructure, and it wouldn't help, say, with transportation, for instance, or any heavy industry that involves mass use of chemical feed. There would be manufacturing bottlenecks. You're still going to need massive, I guess, fusion cells to store your energy.
You need to start with the deuterium making process or gathering process, which is just, heavy water. We get that everywhere. That's easily found. And then this thing can translate it into the tritium that we want to use. Then we go to the next step. And it's the other steps that aren't involved in any of these videos. That's why I keep repeating Helios.
So just being able to generate it by itself, that's a bit of a reach, but it doesn't.
The most discussed
Don't need to.
is muon catalyzed fusion. In this scenario, a muon, which is similar to an electron but heavier, replaces an electron in a hydrogen atom. Because of its mass, the muon brings the atomic nuclei much closer
Did I say... No, I said neutrino detectors. Never mind.
together than an electron would. This proximity increases
Energy with an exclamation
without
point.
requiring extreme temperatures. The effect has been demonstrated in laboratory settings since the 1950s, but it's never been practical. Muons are unstable particles that decay quickly and...
So ultimately you're going to lose more energy. We're talking on the orders of...
Yeah, you can do stuff to make things fuse together and then decay into the parts that you actually want. And overall, the result is, can you make the thing and use materials, use energy, use whatever else, make the stuff that you want to make, and in the end, eventually make power with something that you've developed. What you've proven is you've been able to make tritium without having to use a big-ass electromagnet. Excuse me, I need that. I'm gonna pay you trillions of dollars to vastly outdo anything anyone else is doing, and I will make sure this becomes something that is big enough. The tritium stuff that we want, we're gonna get, and then we're gonna put it into the reactors that actually do the thing. We're gonna have the power that we need without using a lot of power to get to that place in the first place. And that's where we see the real results.
Giga electron volts per muon, whereas previously we've been talking in terms of mega electron volts per fusion, which is energy output more than a factor of 1,000 less than energy
short-sighted
input, which puts us in a similar problem that regular nuclear fusion has, which is an interesting experiment, but it's not a practical energy source, and it's just a little different. I mean, how this works is it shrinks.
The process is like electrolysis. You don't use it to make power. You use it to make it the thing that you need to do the thing. It's just another way of making a thing, a product. The product is then the real use case. We're not even talking about using the product. We're just talking about we're making the product. The confusion was in the process of making the product, can we make energy out of that also? Who cares?
It's the electron cloud.
I don't.
Increasing the probability of fusion.
Producing them in sufficient quantities requires more energy than they can generate through fusion.
Again, if you can take the electron and just strip it away, all those other parts should be able to not need a lot to combine however they want.
That energy imbalance makes muon-based fusion unsuitable for real-world power generation, despite the elegance of the concept. Because of that limitation, most of the serious interest in recent decades
Muons are pretty exotic.
has turned towards solid-state systems. These studies focus on what happens when hydrogen or deuterium is loaded into certain metals, especially palladium or nickel. These metals can absorb large volumes of hydrogen atoms into their crystal lattices. When this happens, the hydrogen atoms become densely packed inside the metal, held in place by its internal structure. Some researchers believe that under specific thermal, electrical, or magnetic conditions, the arrangement of atoms within the lattice could create a low-energy environment where nuclear interactions are possible. The reason this attracts attention is that the metal lattice might reduce the natural repulsion between atomic nuclei. In normal conditions, two positively charged nuclei push each other away, which physicists call the...
I mean, let's say that the lattice is taking the electrons from the rest of the material that you're putting into the lattice. Then, if that's how that's working, that's real simple. And then all you have to do is re-input the electrons, and you have stable nuclei out of the whatever stuff that you're able to use and combining with this. The theory is very freaking simple and sound, and it makes sense.
Coulomb barrier, but
Yes.
in a solid, tightly packed structure. Something quantum effects may allow atoms to tunnel through this barrier more easily, creating rare opportunities for fusion-like behavior.
But the probability is so low, it's still essentially zero, even at
Again, not fusion-like behavior, fusion behavior. It's not like, it is fusion.
scale.
This is not conventional nuclear physics. The theory here is that the metal lattice
Saying it's not traditional nuclear physics implies that it's just not working, because
No.
claiming you're making new physics just so you're...
Again, strip the electrons from the material that you're trying to fuse by putting the deuterium into that lattice. If the lattice wants to take the electrons, then the deuterium and everything else in there that is separate, the gas or whatever the heck you got in there. Also, metal is a thermocouple, so you're not going to have a lot of heat result out of this. And neutrons in a small lattice like this aren't able to just bounce around and go places. They're going to be stopped by all the other material that's around. And they're probably going to hit all the rest of the gas on the way out and recombine.
device would work versus
I say
not.
gas
That
on
just doesn't make any
purpose.
sense.
does more than just hold the hydrogen. It may cause collective quantum effects that allow the atoms to behave differently than they would in gas or plasma. These effects might lower the barriers that usually prevent nuclei from getting close enough to fuse.
And again,
he
it
say
does
gas?
increase the probability, but not by enough that you're going to have a self-sustaining fusion reaction.
In tradition,
That's a sustaining fusion reaction normally involves just a big bundle of reactive stuff reacting with each other. This is a lattice designed specifically to make individual reactions divided from each other, separate from each other, not influencing each other, an entirely separate thing. Not sustained fusion. On purpose. We are making new stuff here. It's a physical process. It's not sustained fusion is the idea. It's there will be continued fusion individual basis.
fusion, overcoming this barrier requires extremely
Usually.
high temperatures and pressures. In LENR experiments, the idea
Again, that is of pure hydrogen and stuff like deuterium. In other words, a single proton or proton with neutron or proton with two neutron, and all of that to say it has the ability with the speed and whatever else to have the electrons go their own way, and maybe everything else. And because of the electromagnetism not being able to hold the neutrons just fly away. If you have sound involved, the neutrons won't just fly away. And in this lattice, the neutrons are basically contained. So they're either going to hit other parts of the palladium, or they're going to hit other parts of hydrogen, whatever parts, causing fusion. Ugh.
Here is that the metal does some of the work by aligning atoms in just the right way. It is a subtle and poorly understood mechanism, but one that has generated enough curiosity to support further testing. Some research groups are now focusing on how to create these rare conditions consistently. Experiments have included using electrical currents, acoustic stimulation, and magnetic fields and thermal gradients to manipulate the behavior of the hydrogen-loaded metals. In some setups, researchers have introduced laser pulses at specific wavelengths to try and induce a response within the lattice. The hope is that triggering the system in the right way will produce a repeatable reaction that yields excess.
Fire is not what you want, and is not what we expect, and is the wrong thing to put on the screen. It's noise for my brain. I hate that you did that, because it's not necessary for the analogy. It's not part of the process.
Heat.
You might as well try shaking the thing to see if it works.
No, because you can use light pulses or laser pulses to change the electrodynamics of everything. We know that if in the double slit experiment, if you put the laser beam across the double slit, it changes how the interference pattern works. It makes it more orderly, meaning that the interference pattern doesn't happen and they just move in a straight line. If you're using those beams correctly, then all of the moving parts will move where you want them to and not in random directions. It can make a more stable reaction. But you don't know anything about the double slit experiment. No one ever does, and who cares? But eventually you will. And in this lattice, it's like a millions slits experiment. Vomiting.
That's essentially what you're doing on the atomic scale, whether you're using a laser or you're using a sound wave
Tyler, you
or
don't
something.
understand.
It's just not reliable. I mean, how would you like it every time you start your car? You have to open up the hood, pull the engine out, give it...
No, it's called a... How do you expect we deal with Bose-Einstein condensate? We're not shaking the damn thing to make it into a frozen ball of goo. We are using electromagnetism in specific ways with pulses or whatever else to make it into a very near as cold as it can get goo. Cold enough you can hold a photon in it. So, no, we're not just bouncing stuff around and hoping it works. There are control mechanisms involved. It is literally manipulating the electromagnetic field so it doesn't make weird patterns, to make weird and different bounces and all that. If they're doing it right. I'm not saying they're doing it right. I'm saying that's what can happen. The fact that you're comparing it to just shaking the box, it's like, that's not at all. That's not at all the thing. And if I was one of those scientists, I would be more bothered by what he just said.
A good shake and then put it back in and maybe it'll work.
Hey, you know what? Sometimes you bump the thing, a thing gets loose or whatever. Let me give you an example. I work with lawnmowers, and sometimes the lawnmower doesn't want to start. Why? I don't know. We don't know. But it has something to do with when I pull on the thing, the reaction doesn't want to go as fast as we want it to. Now, does that mean that there's maybe a gear that's broken a tooth or something, or the injection stuff is not working, or the heat has made an expansion that makes it so it doesn't want to restart again. For whatever reason, but if I give it a good hard tug, the continued motion, which means it just might not have enough oil. The continued motion can make it start up again. So, am I forcing a mechanism to be possibly more worn down and broken as I do that? Tug, which is way harder forces than you ever need to really start the thing. So if you're doing that type of stuff to start it up, maybe you're doing too much, but it might get it to start because you have overcome the friction barrier and it's allowed to continue to move. Because who knows, maybe there's some stuff like some grass that got stuck in there or whatever. I don't know, actually. This cheesecake is delicious.
Few of these tests have shown promising data. Most remain difficult to verify, and reproducibility remains a major obstacle. Another line of thinking looks at the energy barriers inside the metal structure. Even if conventional fusion is not occurring, nuclear reactions of a different kind may be taking place. These might involve shifts in
Again, not maybe. You're getting tritium and hydrogen. It is happening. It's not a maybe.
ratios, small emissions of helium or tritium or other byproducts that suggest nuclear-level processes without following standard models. Several LENR proponents argue that these rare events, even if extreme...
Okay, not following standard models. What kind? Does he mean the...
Okay, you're going off the rail here.
Standard model of particle physics?
Clearly not. That's gotta be a joke.
Because that's its whole can of worms that if you're breaking that, then that's arguably an even bigger discovery than an allegedly unlimited energy source. But he probably is referring to standard models for generating electricity from...
It's not the standard weather model.
Generating heat from fusion, which, yeah, and the simplest solution is you're just not doing fusion because you don't...
We just saw tritium. It is fusion. Stop saying it's not.
Don't have any radiation.
I don't need radiation because literally in these reaction chambers, where's the radiation gonna... In those reaction chambers, the radiation can only go out in certain ways. So it's easy to have the sensor be there. And again, if you're only looking for neutrons, if all the neutrons are being captured and reused, that's not what you're going to detect. So you need a different kind of detector, one specifically for the gamma and beta, whatever radiation that you're getting. I don't know what I'm saying. I don't care. I don't care enough right now. But the neutron part is what you're not going to notice because it's not emitting faster than regular. Again, if it's similar to background radiation or background neutron detection, then good. That means it's pretty safe too.
Collectively generate measurable heat over time. And if true...
Again, I don't care about the generated heat, I care about the products. We already have the products. You're caught up on generating power with this thing. I'm like, we already have the answer, it's a yes. I don't need power from this.
That would mean that energy is being released through a mechanism not yet captured by existing...
Not energy. We can make all sorts of chemical reactions that don't exactly need heat to make things happen, although a lot of chemical reactions are way hotter than anything that we need when it comes to making power. We could make a lot of power out of chemical reactions, but we don't because, one, it's costly, and it burns everything. It uses up all of the reactive material stuff, and we can't recombine it to make the stuff to redo the reactions that we started with. It's a loss constantly. But with this,
look at this. Alright, we're going into sci-fi territory even more.
Just sci-fi representation with pictures that aren't accurate to the actions of what is in the experiments. None of this happens.
Now, one of the most persistent challenges is the mismatch between the reported heat and the lack of radiation. In standard fusion, heat and radiation go hand in hand. You cannot get one without the other. But in many LENR
You can get heat without radiation all the time. What the fuck are you talking about?
experiments, the heat appears without
You can also get radiation without heat. Uh-huh.
detectable levels of neutrons or gamma rays. This matters because radiation, especially neutron emissions, is a
Yeah, gamma rays. So you need a specific gamma ray detector, and if you're not getting the neutrons, that means they're all recombining into the rest of the materials. And yeah, that doesn't even happen with like cubic meters of water to stop the neutrons. So that means you're actually, well, in this lattice, it's much more dense than water, so it's possible they just bounce around and hit something else and become part of that. What if you end up with palladium that has extra neutron that then decays and the neutrons come off later?
signature of nuclear reactions. When atomic nuclei fuse, they usually release energy by ejecting particles.
These guys are probably lucky they didn't do that, because they didn't set up any of the shielding properly, so they would have gotten a nasty dose of neutron radiation if this sort of phenomena did exist.
Particles which we detect as radiation. Without those byproducts, it becomes harder to argue that the heat is nuclear in origin. That is one reason many physicists...
Again, tritium as a byproduct. Who cares? It's still nuclear. It's just not the reactive type. You can't you know that the stuff is being made. Interactions are happening, hydrogen, tritium, whatever. These stuffs are happening. It has to do with a nuclear process. You can't keep saying it doesn't happen. Just the method is different than these other nuclear reactions.
...remain cautious. If energy is being released, but not through known nuclear channels, it raises the question of whether we're seeing a new kind of process or simply a misinterpretation of chemical effects.
Yeah, and the fact that it isn't...
You cannot make tritium from deuterium and hydrogen or other neutrons and make double deuterium into helium, which is the two of them mix smash and literally scissoring each other forever. That thing is not a chemical reaction. That's still a nuclear reaction. You might say, oh, helium is just... If you're going to say that helium is just a compound of 2-deuterium, and you're going to call that a chemical reaction, I'll spit in your face. It's a nuclear reaction. It is a nuclear reaction. You're working with the atoms making different atoms. You're not making compounds. Helium isn't a hydrogen is the tiny thing. Helium, the 2-proton, 2-neutron thing, is not a compound. It's its own atom. The thing that's happening, again, you need to have that work and then have the electrons go back onto the hydrogen helium so that it can become stable. Most likely. Or apparently you can just add more electrons to them so they become regular. Do you even need the electrons in the hydrogen? Again, if you could just take with this lattice, if you can just take the electrons, strip it away, all the interactions will happen The parts just need to bump into each other and it'll happen. That doesn't make a lot of heat.
Reproducible makes me wonder if we're seeing...
It is reproduced. We have multiple sightings of tritium. I don't need any more information. It's proven.
We're really seeing anything at all.
This absence makes many physicists skeptical. It suggests that the heat may be the result of chemical effects, measurement errors, or unknown artifacts. Still, supporters argue that...
Okay, that beaker that is exposed to the air has the capacity of everything in the air affecting the test. So unless that's in a fume hood where it's like non-reactive argon or some bullshit or whatever, I don't want to look at that test and say that could be accurate or something without saying, oh, it might be like, you know, any of the other components that are in the air. Carbon dioxide, oxygen, nitrogen. Is there phosphorus in the air?
We may be dealing with a new kind of interaction, one that sidesteps traditional expectations.
We might be.
The lack of working prototypes adds to the...
What's weird, though, is this new process. It's not consistent with what we...
We don't have a lack of working prototypes. We have the reaction. We have the results. Multiple people have noticed the tritium production. It's just the fact that, yeah, that's not going to make a lot of heat. You're just taking... It's like taking two Lego pieces and putting them together. You're removing the other parts that usually separate them, and yeah, they're just going to fuse together. Because they have the room in that lattice to do so. Increase the size of the lattice for some reason. You should be able to make even bigger things out of it. Hell, if you stripped all the electrons off of uranium, you could fuse those together. And, by the way, you need something the size of maybe 1,000 proton, 1,000 neutron to make the next shell, and then that needs enough electrons added back to it to help hold it together. Except for the electrons are going to want to be pulled in to the thing. It doesn't work well. It's not easy to do.
Have observed in actual fusion reactors we've been able to do on Earth, such as using tokamak.
So the way, it's not just regular electrons, you have to have a photoelectric effect that allows the electron to bump up to the higher shells, which are basically the highest shells of a small atom, are so close to everything. The biggest shell, the smallest shell of the big atom is bigger than that smaller thing. So it wants to naturally flow into that. The repulsive force isn't enough to do it. So you end up with the electron tunneling. That makes sense because it just naturally would be that close if there wasn't enough repulsive force. Or if you didn't shoot the electrons with enough photons that they end up speeding up enough to be able to go around fast enough so that they aren't falling into the atoms themselves. And at those speeds, the electrons don't want to do stuff, so what happens is they collapse, the thing separates, and the amount of energy necessary to hold the electrons on the outside is a lot less.
Or stellarator designs, or the National Ignition Facility. So this would
That's why uranium turns
require
into lead.
rewriting nuclear physics from scratch while somehow...
Yeah. Again, you still aren't holding neutrons with sound. The general thing, the only thing that can hold because it's not a positive or a negative thing, you can't hold it with electromagnetism. You have to use sound. If you're not doing that, you're not doing science. You're just being inaccurate. You're going to have inaccuracies. You're going to have neutrons just flying off stupidly.
How leaving every accelerator and reactor experiment intact in the process. That's pretty unlikely.
Uncertainty. No laboratory has produced
I've made my case.
a system that generates continuous reliable energy on demand. There are test rigs that have shown energy output above input levels, but these results fade quickly and often fail to appear under repeated trials.
Yeah.
Even
Making energy out of it, if that is a byproduct, means for increased efficiency. Means less energy that you have to initially put into it in order to keep on making more of it. However, if it's not the process that you need to be doing in the first place, Helios did an entire thing turning the deuterium and hydrogen, fusing into tritium and helium, and their process involves a massive warehouse of tiny amounts of charge in big vats of liquid that are holding bits of charge. These capacitors all combined to make a massive jolt of electromagnetism in the core of this reactor thing to make all this other stuff happen. And what you're saying is all you have to do is just strip away the electrons in this lattice thing, because yeah, that's the only thing in the way. And you got it. The science, unfortunately, is sound. You're just not grasping it. I'm sorry.
well-funded labs with high-precision instruments have struggled to replicate promising data. That inconsistency is what
Their
keeps
precision isn't
LNR
nearly high
on the
enough
fringe,
for my
even as
standards.
small signs of progress continue to emerge.
Order of magnitude.
Like what? Progress being that they're actually going to use a control group and bring in proper
We're
detectors.
going to actually be making tritium on a mass scale easily without having to worry about radiation, because holy crap. Also, we're not even going to use a lot of power to do it. Holy crap. This is great.
Because that's the main difference I've seen.
Researchers in the field, they're not discouraged. Some of them believe that the problem is not the science, but the control systems. In other words, the effect may be real, but it's extremely sensitive to small changes in materials, environment, or experimental setup. And if that's true, the next step isn't a reactor. It's a better understanding of how to reliably create the conditions under which LENR might take place. That requires
Again, you're trying to make power out of it. Good for you for hoping that will ever happen. But we're still making fusion. We don't care to make power. And we will continue. And the stuff that we have will make the power. The fact that you didn't... Tyler, you've seen the Helios video. You should have referenced it as many times as I did, or at least once.
improved instrumentation, more standardized protocols, and careful
That's not a bad idea.
Yeah.
long-term studies that are not rushed to publication. The potential payoff remains enormous. If even a fraction of the claimed heat outputs are real and repeatable, they would represent a
I don't care about
fundamentally
heat.
new source.
And again, I rest the point of no, it wouldn't. If it did somehow work, it would be cool, but it would be in the same category as hot nuclear fusion on Earth.
Let me explain something to you again about this thing if you didn't catch it from the first time I said it. The energy, what they're doing is they're taking the deuterium, putting it into this lattice. The lattice is like a mesh. That mesh, like any, you know how you have those grids where the cooling happens, you got fans, you get all the heat into this heat exchanger, and all the heat goes into that, and because of the fans, it dissipates immediately. These reactions are happening in similar ways, where if heat can't build up in this mesh, it won't build up. You might be using the wrong type of material to allow for heat to build up. And again, you think about it. If heat is the movement and wiggling of all of the materials together, if you end up with a mesh that is genuinely stable and structured to be solid, then it takes a lot of motion and stuff to make the certain amount of specific heat, but everywhere. And the amount of reactions you're happening per small section can easily dissipate throughout the entire mechanism. Or possibly just directly burn it away. Like we saw, there was a plate that was like held up at some point. This little thing here. Where the fuck is it? That.
Especially palladium or nickel. These metals can absorb large volumes of hydrogen atoms into their crystal lattices. When this happens, the hydrogen atoms become densely packed inside the metal, held in place by...
This is literally a nuclear process that is happening. And yeah, if you have enough stuff that can attract the neutrons or combine with the neutrons to make something else, then you're not going to end up with a lot of spare neutrons just doing stuff. And the muons, well, we don't care what happens to them, to a degree.
Its internal structure. Some researchers believe that under specific thermal...
That exact picture is all I need.
The arrangement of atoms, hydrogen atoms become densely packed inside the metal, held in place by its internal structure.
Yeah. So if we can end up with stuff like the tritium, the helium nucleus, or enough materials in the mix together that the deuterium turns into more tritium, we won't have, or it turns into more helium nucleus. If we can control all of those numbers, we don't need to have excess neutrons. And the more excess neutrons that we have, because we're not controlling them with sound, then we're going to end up with less tritium and helium out of all of it. So less reactions in total. That's what we got to do. Make it so that the numbers are good enough that we can work with all the resulting materials without having excess neutrons. Again, I don't care what happens to the muons. It's only the electrons that matter in that. And again, you're not realizing that this can happen on the size of a microchip.
Some researchers believe that under specific thermal, electrical, or magnetic conditions, the arrangement of atoms within the lattice could create a low-energy environment where nuclear interactions are possible. The reason this attracts attention is that the metal lattice might reduce the natural repulsion between atomic nuclei. In normal conditions, two positively charged nuclei push each other away, which physicists call the Coulomb barrier. But in a solid, tightly packed structure, something quantum effects may allow atoms to tunnel through this barrier more easily, creating rare opportunities of fusion-like behavior.
But the probability is so low, it's still essentially zero even at scale.
This is not conventional nuclear physics. The theory here is that the metal lattice...
Saying it's not traditional nuclear physics implies that it's just not.
Where is that little plate that I saw? The little disc of something? Because that was neat, and I liked the look of it, but I don't know where that is anymore. Does it... Oh, I don't remember where the heck it was. I should have paused at every instant of BS that happens.
That uncertainty makes it frustrating, but it also makes it compelling. The search continues not because it has already succeeded, but because it has not completely failed. And that's enough to...
I don't. As an engineer,
It's because the people analyzing it are not using their full head. You still don't know how electrons work. You still don't know how electromagnetism works. You still don't know how... Yeah, if you separate all the parts, then all you need to do is combine the bits. And if the lattice also makes a pressure system, then by just squeezing it and just pushing it all in there with like a injection pressure thing, then yeah, you'll just end up with fusion actions. There's not much else you need to do. The reactions will be random, and if the reaction chamber is big enough, then you can start making bigger things for some reason. Go beyond helium. End up with materials that are in whatever other range. Magically make carbon for no reason.
Not getting repeated results is a failure in and of itself. Now,
The tritium is a repeated result, so success.
I'm not dismissing if someone is interested in studying LENR, please go. Go right ahead, but just do it from the lens of you're curious about...
It's gonna be the recreation of material, not generating power.
chemical interactions. You're just from a pure sense of
It's still nuclear.
curiosity and about wanting to
saying
see
it's not.
how it interacts with palladium or whatever, rather than I'm got to prove it to uphold the hype or whatever, because that sort of bias going into it just isn't good for any sort of scientific experiment. And hey, I will fully accept to be proven wrong if someone does it.
I mean,
That
that's-
would be a cool thing to be wrong about, if there really is something there, and the implications.
yes, but we all know that that's just a catch-all to say, hey, you know what? If I'm wrong, I'm wrong. But it doesn't. It just means that you don't know, and that's fine to say that you don't know.
For greater physics and greater engineering. I'm just not convinced yet.
We keep a small but determined group of scientists asking one simple question. Can it really work?
Where's that heat coming from?
Verdict: no.
Now, after more than 30 years of research, cold fusion remains unresolved. It has not been proven, but it hasn't been fully disproven either. Most experts still view it with deep skepticism.
You could argue it has a very low probability of appearing to work if you just take a bunch of quantum tunneling into account, the same non-zero probability of quantum tunneling phasing through the entire Earth. And
Again, quantum tunneling is about electrons doing stuff. If we're just taking the electrons out of the picture, we're just making those proton-neutron masses do their dances, and then we end up with new materials. That's totally valid. And quantum tunneling through the Earth, you're not made up of electrons. It was a ridiculous statement in the first place.
entering from the other side.
Does quantum tunneling happen with anything other than electrons? Does it happen with hydrogen? Yes. Because that's why there's, or even helium, there's helium leaks and stuff, because you can only make things so big, and the nucleus of a helium or hydrogen is only so good
And
that you don't really end up with a perfect seal, even if, like, unless you use, like, diamonds and stuff. And then it's gotta be, like, the space between diamonds or something. And it's not perfect. You could also use carbon nanotubes, but that's only going to give you so much pressure. Helium and hydrogen under pressure is going to escape the vessel. That's just how it is understood to be.
not practical.
But the idea never completely disappeared. It continues to surface in new experiments, quiet funding rounds, and occasional calls for reconsideration. What makes this story unusual is not the scale of the original claim. Science often produces bold ideas that turn out to be wrong. What makes this different is the persistence of small results scattered across decades that refuse to fit cleanly into any existing theory.
Yeah.
A growing number.
It's the number of questions that we got to solve, and then we have, people like me who can maybe put some headway into it. But the problem is I'm not there. I need to be there. That's where I really need to be, not just on this chair. Doing... The fuck is this? Where did this come from? I don't know what this is. What is this? This came from nowhere. It's not part of my cheesecake, for sure. The fuck? I'm very confused right now. Nothing explains whatever the frick this is. There's writing on it. What the fuck is this thing? What is this thing? I don't know what the fuck this is. Like, it looked like something related to medical, but it definitely didn't come in my cheesecake. I don't know what the fuck. No, I have no idea what the fuck this thing is. It was just randomly in with my sheets, and I'm like, it doesn't match anything that I can think of. It's like not part of a straw or whatever the fuck else. I'm thoroughly freaked out. Let's move on.
Of respected scientists have said it is time to take another look. They are not promising success. They are not saying.
I don't know. To me, that sounds like an appeal to authority. I'm going to be cautious about that. They could just be interested in it for other reasons. Who knows?
Cold fusion will work. But they believe the question has not been answered yet. And they argue that ignoring unexplained data simply because it comes from a controversial field does not reflect good science. The
Yeah.
logic's simple. If the effect is real, it deserves careful study. If it's not, then testing it again will help close the question with confidence.
That's fair.
Either way, progress comes from evidence, not from reputation.
Again, you take away the electrons, what is really stopping the stuff from becoming deuterium and tritium and turning into tritium and helium? And then again, if you can repeat that but on a larger scale, who's to say you can't just transmute any materials into any materials? And why is there blood in my hair?
LENR research still faces serious challenges. The data's inconsistent, the theories are incomplete. No working device has been built. But if it never works, well, then it belongs on the list of
Why
those
is there
curious
blood in my hair?
and stubborn scientific questions of the last century, a mystery that refused to disappear, even when nearly everybody stopped looking.
I don't know. When I clicked on this, I was expecting if there was some idea, if there was another Pons Fleischmann emerged, even if it was another crackpot experiment, but this just kind of seemed like a rehash of stuff from 35, 40 years ago.
It's because the propagation of the tritium, the whatever else, the whole idea of that stuff is still like, how is it happening? What can we use it for? and we already know that there's a use for it because of Helios. So by the way, I'm not making this up. I don't know why there's blood in my hair. Or I don't know why there's a weird whatever the fuck this is. I've scanned my brain for like dozens of different things, and I can't think of anything that it would be from. It's not from any drink or whatever else. It's like, huh? But the blood is the weirder thing because I'm like, what?
So I don't think a whole lot of progress has been made. Thanks so much for the recommendation. Thanks so much for watching. I'll see you next time.
I mean, I'm okay, but whatever. I don't know.
I was gonna have to pour it, and
Okay, so, again, the connection between electrons and the rest of the matter is the electromagnetic field. You mess with that, and you don't have anything else. And the main thing is, like, with normal atomic particle stuff, there's an interaction between the protons and the neutrons that make them fuse together in the first place. So, what is that thing to begin with? And they say it's the weak nuclear force or the strong nuclear force. I'm sorry that I don't have it in my head about which one is which. Bear with me. But it's that thing and that interaction. So the fact that we're getting helium is that interaction will naturally occur as long as the electrons are not there to provide the barrier that normally is cycling around the atoms to make it so that, like, you realize, again, what you're not remembering is that electrons go around an atom like a quadrillion times a second. I get that number because of 2.2 thousand kilometers per second is the speed of an electron. Convert that into 1/10 of a nanometer, which is the size of the diameter of an atom, and you end up with 22 quadrillion atomic whips per second. That's how far an electron goes. That's how fast it goes. So if you take that type of thing, and again, I can show you the picture that I have. I love this picture. Right? Though that super speed electron, these are just two electrons, and the reason why they like to go in one spin up and the other one spin down is because the electromagnetism likes to flow through them both. And so what you end up with is those electrons are moving with spin up, spin down in this direction, in this picture, that direction, with the other picture, this direction again, but there's more of them. Again, 2 electrons, you got 6 electrons, who cares? And you end up with another 6 electrons going the other way, in this direction and in this direction. So with this information, you can tell the moment you remove those electrons, there's nothing in between the atom, which is the proton-neutron pair, and the other atoms. Right? You get rid of those electrons by putting them in the lattice, and you have fusion abilities, which is why we end up with the tritium. It's an interaction that's like, yeah, you take away the barrier particle, the electron, and boom, you have it. Why is this hard to understand? I don't get why it's hard to understand. Right? You got 2 electrons, you got more in a different thing and pattern. This is my favorite picture because it well illustrates the fact that there are so many echoes. The electron goes, again, quadrillion times around an atom every second. Easily. That number, give or take a bit, doesn't matter. It's a lot. So, yeah, if you remove the electron and you put it to that lattice, that hungry lattice, right, and you only end up with the proton-neutron pairs, then fusion is easy to happen because there's no repulsion, just the positive parts able to bind naturally and create their own interactions with the neutrons that are around. And with enough pressure, that'll just normally happen. And with all the other electron stuff that's happening around it, they can't bind with anything else besides each other. So you end up with the deuterium and all the protons and neutrons from that. You end up with the tritium, which has the extra neutron, and the proton just goes off, and you just have the hydrogen on the end of that, and you end up with the helium, where the 2 deuterium merge together. The 2 plus 2 equals 4, very basic. There's no negative out of that. And then you end up with the 2 deuterium that create the tritium, but you end up with a neutron that decays into a proton? No, that doesn't happen. Proton decays into a neutron is possible stuff, and you can end up with excess neutrons. But yeah, the blood is like, why? What is happening? But that's the thing. It doesn't have to be recent blood. It could have been old blood from... But I just had a shower. I didn't bonk my head during the shower. So I'm not expecting any recent thing. Like, it could have just been a clump that was there, but I don't know. But it seemed red, so that red means recent. Because it would have, if it was old, it would have turned to brown, right? Because oxidate. It was oxygenated. Anyway, so yeah, if you don't understand how this works in the fundamental functions of how atoms work, the only reason they're repelled at all is the electrons, then yeah, you can do fusion without any of this stuff. You've been wasting a lot of power. You could easily have done it a different way. So much simpler, so much easier. All this stuff. This is a different video. Who cares? I'm not reacting to this. It's not important. It's just funny. And I have seen it. And it's fine. I haven't given a like or anything to it because I've seen the Nile Red video. Where it's like, wait, no, I have seen this. I have reacted. Wait, hold on. How have I? I'm sure I would have sent at least a comment, but I haven't done a video reaction to this. Maybe I haven't commented either, but I saw it and I may have had no notes because it's just him talking about bromine, and then he starts off with, no, that's soy sauce. That he broke a beaker of it. It's like, you would not do that. And it was funny, but there's nothing. I could do a reaction, not in this video. Making dangerous chemical in his parents' garage. Nuclear engineer reacts. Fun times. Look, listen. Here's the thing, right? If you don't know how fusion happens in the first place, besides the fact that the neutron's going fast bypasses the electron repulsion in the first place, that's how you get normal fusion. Remove the repulsion, you don't need the neutrons to violate anything, and you don't end up with this random stuff. So again, you work with fission. I'm not going to judge you on that. You can know about fusion just as much. It's just, yeah, this is low energy stuff. We're getting the tritium. It all makes sense. So unfortunately, that's your thumbnail. And whatever. Yeah. Yeah, it's a good video. You should watch this one because it's just fun. It's just fun. It's dangerous. But Nile Red has his stuff together. There is no comments. But yeah, for those of you who thought about this, thanks for hanging out with me. I like it when you do. I wish you would learn to use sound in your reactors because standing waves are the only things that can hold neutrons. If you don't do that, you're dumb. End of story. You just are. Like, just expect yourself to be inefficient. Expect neutron reactions and neutrons flying at you, causing damage, and all this junk. And, I mean, again, radiation only... What if you end up with radiated, whatever the polonium or whatever it is that you're using as the lattice, right? And how easy is it to make that material? Can you do it en masse? I don't know. But the main thing is, I think it has the extra electron shells, so it wants the electrons. So it strips away all the electrons from the rest of the stuff, and that's why it's able to make the reactions that it does. And without that much electrons, you would still end up with some that want to hold on to their own electrons and do their own thing. So everything else bumping into those electrons, yeah, you're going to end up with some heat. And if you don't understand that, you're a bad scientist. Bye.